In the next section of this module, we will be discussing the compressed air. Compressed air systems require a substantial amount of kilowatts or shaft power in order to produce compressed air. Compressed air is generally considered free, and because it's clean to use, it can be stored and no real hazards associated, except a few safety hazards with the use. Widespread lack of energy management opportunities and awarenesses and wastage is very high on compressed air, meaning there's no understanding how much compressed air is really costing your organization. So if we compare this with insulation, when you feel heat being transmitted from a pipe, for example, it's quick to insulate. For air losses due to air leaks and dirty air filters, it only gets attention when it interferes with the operation of the plant. We see pressure drops of up to 40% at the end users, and oversized compressors are installed. The annual cost to operate can exceed the purchase price of a compressor. So let's have a look where the energy goes in compressors. When we look at energy, the majority of the losses are associated to heat losses. When we look at air, the majority goes to the end users, but a lot of air is lost due to leaks and inappropriate uses. Looking at a Sankey diagram in order to illustrate the losses, we can see that major losses are associated with heat losses, and only 15% of useful energy is used. There's a few different types of air compressors: dynamic, positive displacement, rotary screws, reciprocating, and axial compressors. Compressors installed at Formosa Textiles is mainly rotary screw compressors. So we've got three main sections when we come to compressed air systems. We've got the compressors, the compressor plant, we have the distribution network, and we have the services. Let's now consider potential opportunities. First of all, we can reduce the system operating pressure. Formosa Textiles at some places had 8 bar pressure, and the main requirements are for pneumatic users and cleaning of overalls and face masks, which first of all is an inappropriate use. 8 bar is not needed for this. We can reduce the pressure systematically with half a bar until we can stabilize and determine what the minimum requirement is for the plant usage. Remember, 1 bar pressure drop reduces all leakages in the system as well. Approximately 1% energy is saved for every 15 kilopascal drop in air pressure. If we repair air leakages, we reduce wasted compressed air. It is the greatest single cause of energy loss, up to 40%. It's masked by the plant noise, thus difficult to determine. The total elimination of it is impractical, but we can get to a maximum of 95% operational. We can quantify by conducting pressure drop tests, meaning we close all end users, start the compressor plant and switch the compressors off and observe the time and the loss in pressure. We would also need the complete volume of compressed air lines and accumulators. As an example, a 1 millimeter hole is equal to 1 liters per second at 6 bar and requires 0.3 kilowatt. That results in 150 US dollars or basically rands a year if we're working on 10 cents per kilowatt hours. In Formosa's case, a 1 millimeter hole would result in a 400 rand a year cost. So multiply these by a number of leaks, and leaks up to the size of 10 millimeters and this becomes a major contributing cost factor. If we look at electrical motors and how we can reduce energy on them, we can highly likely replace them with highly efficient motors. Motors that have been rewound have lost a lot of efficiency. You can also ensure that the correct type of motors and the correct pole motors are installed. We can use smaller motors at high capacity, and we can install VSDs on the compressor air system. We can reduce the compressor inlet temperature. Remember, cooler air is equal to more denser air. Thus, power consumed by the compressor is proportional to its specific volume, which is proportional to the absolute temperature of the air. Ensure that all filters for air is very clean. We can also reduce the compressor outlet temperature. Remember, the air in the compressor rises to 250 degrees when the compressor is compressed adiabatically to just 7 bar. Cool air after compression by water and air reuse somewhere else. So let's catch that heat and use it for hot watering system perhaps. We can increase compressor's inlet pressure. We can determine if heat recovery is possible, and we can consider alternatives. For example, compressor is not needed to clean off face masks and overalls. A blower would more than suffice and use a lot less energy.